Welcome to a new session of electrical machines. In today's class 3 under transformers, we are going to see a transformer on load conditions. In our previous class, we have seen the principle of working of transformer. Apart from that, we have also seen the derivation of EMF, and we have derived EMF, which is given by E1 equal to 4.44 and 1 F B max A, or simply B max A can be replaced by flux phi max. So this we have seen in the primary winding as well as in the secondary winding. The formula changes to this: E2 is equal to 4.44 N2 F B max multiplied with the area of the cross section. So what we have seen on no load conditions is that voltage V2 is equal to E2 in N2. N2 is the number of turns, E2 is the EMF induced in the secondary winding, and V2 is the measurement across the output terminal. Whereas V1 is the supply voltage, and because of V1, I0 current is flowing in E1, and E1 is in opposition with V1, whereas E2 is equal to V2. So this we have seen in our previous class. So if at all we draw a phasor diagram, it would be like this: E2 is equal to V2 on one direction, whereas V1 is equal to minus E1 on the primary side, and the E1 and E2 are in the same direction, whereas the opposition, you have IE, which is equal to I0 cos phi naught in one direction, and IM is equal to I0 sin phi naught in another directions. With the help of these two, we can get the value of no load current, which is nothing but I0. Now this current is at angle phi naught with respect to the input voltage or the primary winding. So this, what we can understand, that a no load current is a composition of active component and it is a composition of magnetizing component. What exactly is I0? I0 is nothing but the exciting component. It is very small compared to the full load primary current, which is almost equal to 2 to 5% of the full load primary current value. And I0 square R1 is a loss in the core, which is very small and can be neglected also. So these basics you should know before we are going to understand the actual transformer on load conditions. So active energy component, that is nothing but IE is used to meet the iron losses in additional to small amount of copper losses that occurs in the primary winding. And we have to remember that IE is in phase component of the system input. And the quadrature component, or we also call as watt less component or magnetizing component, it is used to create the alternating flux in the core. So if at all you look into this particular diagram, you can see we have V1, which is supplying the no load current I0, and this is the composition of the active energy component IE and the quadrature component IM. Now this nothing but it is R0 and X0. We are treating the value as resistor and inductance, reactance, which are nothing but a kind of RL load at no load conditions. Now V1 is equal to minus of E1, what we already have seen according to the Lenz's law. And if at all you draw a triangular diagram of current, you're going to get in this fashion, where the IE component and IM component are in respective of I0 cos phi naught, I0 sin phi naught. You can estimate with the triangle shown over here. And the magnitude of the no load current is given by under root of IE square plus IM square. And the angle between these two is given by phi naught, which is equal to tan inverse IM by IE. So these conditions, you should remember that when the transformer is on no load, all these conditions are present in the transformer and which are of very small value. Anyhow, when you take actual transformer on load, once the load is connected, current I2 is flowing into the load, and that load we are treating as an impedance load, which is a composition of real values as well as the imaginary values. The imaginary values are because of the inductive capacitance or inductive uh, inductance, or due to capacitance. What I am trying to say is the reactance component is due to the inductive coil nature or the capacitive coil nature. Anyhow, when you talk about the transformer, the basic EMF formulas and the transformer ratio formulas, you have to recall the magnitude and phase of secondary current with respect to the secondary voltage V2 will be depending upon the characteristics of the load. What kind of load we are talking about? We're talking about the current I2, which will be in phase with V2 when the load is non-inductive, what we call as the resistive nature of the load. And I2 will be lagging V2 when the load is inductive, and I2 will be leading voltage V2 when the load is capacitive in nature. Now, when you take the diagram of a transformer, this is how we see the windings, and when the load is connected, IT is also flown over here. Then the measurement of load voltage is nothing but V2, and when we treat the concept with ideal transformer, so for different types of loads, when there is no load, we know that the no load, the transformer draws a no load current I0 from the supply mains, and this current sets up an magnetic motive force of N1 I0, which produces flux phi, and that flux phi is responsible to linking with the primary as well as the secondary of the coil due to the mutual inductance. Now, once the flux is flown, the secondary receives the voltage as EMF E2, and the measured voltage can be obtained across the terminal as V0. Now, once the transformer is loaded, you can see when the transformer is loaded, already a flux is set up, right? But this loaded transformer makes current I2 to flow through it, and this current is flowing in the secondary of the winding, and it is responsible to introduce a motive force, magnetic motive force, which is responsible to generate a flux phi 2, which is in opposition to phi according to the Lenz's law. Now, after this load is connected, as I told you, current I2 flows through it and sets up its own MMF, and hence creates a flux phi 2. As I told you, this is in opposition of the main flux set up by the primary no load current. And as I told you, this is in accordance with the Lenz's law. Then what happens? Then phi 2, that is the newly flux, weakens the original flux momentarily. So primary back EMF tends to be reduced. So once EMF is reduced, the difference of the applied voltage V1 and back EMF E1 increases, and therefore more current is drawn from the source of the supply flowing through the primary winding until the original value of the flux is obtained. So it gets keep on repeated until the original value of flux is obtained. So that original value of flux, as a result, again causes increase in the back EMF E1, and it adjusts itself as such that there is a balance between the applied voltage and the back EMF. Now what happens with this? Let us assume that the additional primary current is I1 dash, which is taken from the supply. This is in phase opposition with the secondary current I2, which is already over here, and is called as the counterbalancing current. This counterbalancing current sets up N1 I1 dash, producing a new flux phi 1 dash in the same direction as that of the main flux, and cancels the flux phi 2 produced by the secondary MMF N2 I2 being equal in magnitude. So you can see flux line, which is shown by this dotted phi dash. Now this is cancelling the phi 2. So N1 I1 dash is equal to N2 I2 dash, which implies I1 dash is equal to N2 by N1 multiplied with I2. The total primary current, therefore, is a phasor sum of the primary counterbalancing current I1 dash and no load current I0, which will be approximately equal to I1 dash, as I0 is usually very small in comparison to I1 dash. Now, if that is true, I1 will be equal to I1 dash, and which is equal to N2 by N1 I2. Now we can see the secondary flux is terminated by the I1 dash sets up the flux, which is I phi 1 dash. That two fluxes are cancelled out, and I1 by I2, which is equal to N2 by N1, remains as a constant. Therefore the main flux remains same. So this is how the transformer, when it is loaded, it takes care of these conditions. Now that load can be resistor, inductor or capacitor. So while drawing the phasor diagrams, in order to understand, we have considered V2 is equal to E2 and V1 is equal to minus E1, right? The secondary current is in phase, lags behind, leads the secondary voltage V2. Three conditions. When the voltage across the output terminal, uh, it is uh, shifted by an angle phi 2 for resistive, inductive and capacitive loads respectively. Now you can see for a resistive load what we have to do. When we're drawing the phasor diagram, I have taken flux on one x direction, and you can see I have selected V2 equal to E2 and V1 is equal to minus E1. Okay, now I2 is in the same direction for the resistive load, and I0 is the no load initial current. Fine. Now in order to counter this I2, we have I1 dash. Fine. Now with these two, I0 and I1 dash, the vector results in I1, which is nothing but the primary current. So this is a phasor representation of resistive load when transformer is on load condition. The angle between I1 dash and phi naught we are treating as phi naught, and phi 1 is the angle between I1 dash and I1. So this is treated for unity power factor, means when the load is completely resistive, it is treated as a unity power factor phasor diagram. Now for lagging power factor means what? When the load is inductive in nature, what is going to happen? So same, we are taking the flux on x direction, on y we have the voltages. So we know that V2 is equal to E2 and V1 is equal to minus E1. Now I0, we know that it's a no load primary current, and I2 is nothing but the current which is lagging the voltage V2 by angle, which is angle phi 2. And to counter I2 we have I1 dash. Now the vector addition of I0 and I1 dash results in primary current I1. Now already we know that there is the angle between the V1 and I0 is phi naught, and phi 1 is the new angle between I1 and V1. So you can see in the resistive load under unity power factor, the I2 direction and V2 direction are on the same line, whereas in the inductive load, the I2 is shifted by phi 2 with respect to V2. Now what happens for the capacitive load? For the capacitive load, same, we are taking the x and y directions like this, and I0 we know that it's a no load current, and I2 is at angle phi 2, which is leading the voltage V2. Now to counter I2 we have I1 dash, right? Now when you take the vector notation of this resultant of I1 dash and I0, we get I1 in this direction. And again the angles which are framed, that is phi naught is between I0 and V1, and phi 1 is between I1 and V1. So this is how the phasor diagrams are drawn, and that is how we study the voltage and current conditions of the secondary with respect to the primary. So I hope you like this particular class. Please share among your friends, subscribe to this channel and press the bell icon for the future notifications. Thank you.